Troubleshooting is probably the most challenging aspect of your job as an electrician. Your know-how and experience are really put to the test when electrical problems arise. Electrical problems can occur in any type of circuit, whether it's in a specific piece of electrical equipment or part of a much larger electrical system. Because an electrical problem can arise from a variety of sources, it's critical that an electrician be able to pinpoint the cause of the problem quickly and minimize the effects that it can have on the circuit. An electrical problem can have a wide range of effects, ranging from having to use a similar piece of equipment in another location to unwanted downtime, systems that do not operate properly, equipment that's damaged or destroyed, and most important of all, hazardous conditions that can injure workers, or worse. To avoid these effects, electricians are often called upon to troubleshoot problems in many different types of electrical circuits. Troubleshooting is a challenging, high-stakes endeavor, and it can be frustrating and difficult. But done well, it can also be one of the most rewarding aspects of electrical maintenance. Electrical problems may show up at any time and anywhere. Some problems are as simple as an abnormal signal value that can be corrected by a minor adjustment. Other problems are not as easy to identify and correct, especially when the cause of the problem is in a non-electrical component or when it's in another system. Regardless of the cause, electricians are responsible for zeroing in on problems whenever they occur and bringing things back to normal. A good way to ensure that the proper actions are taken in response to an electrical problem is to follow a troubleshooting procedure that is both systematic and logical. In simple terms, troubleshooting is the process of detecting a problem, determining its cause, and taking corrective action. The troubleshooting procedure that we'll use in this unit is divided into 5 major steps. Depending on where you work and the nature of the job, the exact procedure that you follow while you work on problems in electrical circuits may be slightly different from what you'll see here. Just keep in mind that the underlying principles are the same. The 5 steps of our basic troubleshooting procedure are identifying the problem, taking preventive action, determining the cause of the problem, correcting the problem, and returning the circuit to normal operation. The first step of our procedure, identifying the problem, includes recognizing that a problem exists and observing its symptoms. To perform this step, an electrician can use many sources of information. Alarms and annunciators can give visual or audible warnings of possible abnormal conditions. An automatic shutdown can also indicate a problem. In addition, a routine inspection could reveal a problem. Another sign that may indicate a problem is a signal value that is not within its normal range. Once a problem has been identified, the next step in our procedure is to take the immediate preventive action necessary to keep it from becoming worse and causing injuries or damage. It's important to note that taking preventive action is not the same thing as correcting the problem. Preventive action is a short-term action that's meant to put a circuit in a safe condition while work is performed to correct the problem. For some problems, the only way to prevent damage is to initiate an emergency shutdown. For others, you may need to switch the circuit from automatic to manual control, bypass a piece of equipment, or start up a piece of backup equipment. Before you take any preventive action, though, it's critical that you consider the possible effects of the problem and your actions on other personnel and systems. For example, you may need to notify personnel in other areas that there's a problem that could affect their safety or the work that they're doing. After the appropriate preventive action has been taken, the next step is to determine the cause of the problem. Determining the cause of a problem is essentially a process of elimination, separating those factors that are not causing the problem from those that might be causing the problem. This often requires that you consider a number of things. For example, was the change in the circuit's operation abrupt or gradual? Is the problem intermittent or constant? Have there been similar problems in the past? What was the condition of the circuit? Did the problem occur while the circuit was in a steady state condition, or was the circuit in startup or shutdown? Answering questions such as these can help determine the cause of a problem. For example, suppose a system had been working properly in its normal mode of operation, but during a change to its bypass mode of operation, it failed to start up. The cause of the problem in this system is probably in the system's bypass circuitry. To be able to determine the cause of a problem in a circuit, an electrician must fully understand how the circuit works. Many sources of information are available to help you determine how a circuit normally operates. Electrical diagrams can help you identify a circuit's components and how they are electrically connected. Using these diagrams to trace current paths through the circuit is one way to determine how the circuit is supposed to work. You may be familiar with a system's operation from your own experience. If that's the case, you can draw on that experience to make troubleshooting less complicated. The person who operates the system can be an excellent source of information as well. From working with the system on a daily basis, that person should be quite familiar with its normal operation. Plant supervisors can be another good source of information on how a system is supposed to work. Many of them have worked their way up through the ranks, and they often know a lot about the normal operation of the facility's equipment. After the cause of a problem has been determined, the next step in our troubleshooting procedure is to correct the problem. Correcting the problem can include making adjustments and repairing or replacing equipment. In some cases, correcting a problem may require the assistance of instrument technicians, maintenance mechanics, or operators. After corrections have been made, the circuit can be returned to normal operation. For an electrician, returning a circuit to normal operation usually involves reversing any preventive actions that were taken during troubleshooting. It may also mean working with operators or other personnel to make sure the circuit operates properly, and notifying the appropriate personnel and other affected units that things are back to normal, so that they can make adjustments at their end. It's also important to properly complete any paperwork associated with the problem. Let's stop here and try a question on the basic troubleshooting steps that we've just covered. Troubleshooting is usually based on a process of elimination, that is, separating the factors that are not causing the problem from factors that might be causing the problem. Electricians commonly separate these factors by making voltage checks. Voltage checks can be made with a variety of testing devices. In this unit, we'll use a multimeter that's been set up to function as a voltmeter. We can see how making voltage checks can eliminate possible causes of a problem by using this illustration, which represents the control circuit for a piece of electrical equipment. This illustration contains 4 blocks. The block on the right represents the circuit's load, which uses electrical power to do work. Common examples of a load include motors, control relays, and lights. The other 3 blocks, which are labeled A, B, and C, represent devices that control the operation of the load. Common examples of control devices include push-button switches, limit switches, and relay contacts. This circuit's operating voltage is applied to the circuit through the line labeled L1, and the circuit is connected to neutral through the line labeled N. To make it easy to refer to various locations in this circuit, we'll add these numbers. And to show how voltage checks can be made in a circuit, we'll use this representation of a voltmeter. The voltmeter has 2 probes that connect the instrument to the circuit. The voltmeter's display indicates the result of each check. To check voltage at any location in a circuit, the voltmeter's probes must be connected to the circuit. Connecting the voltmeter to the circuit forms a parallel connection between the voltmeter and the circuit. This means that any voltage present at the test point being checked is also present at the voltmeter's probes. In this unit, we'll show the voltmeter's red probe connected to the test point that is being checked. The black probe will be connected to what is called a reference point. A reference point is simply another point in the circuit to which the test point being checked is compared. As an example, let's use the voltmeter to see if voltage is being applied to the circuit. To make sure this circuit has the proper operating voltage, the voltmeter's test probe should be connected to L1 and neutral. With the voltmeter's test probes connected, the voltmeter's display indicates full line voltage. This means that voltage is being applied to the circuit. It's a good practice to make sure that a circuit has voltage applied to it before you start checking the circuit's components. Generally speaking, whenever a voltage check indicates the presence of voltage, it means that there's a complete path through the circuit to the test instrument's probe, through the test instrument to its other probe, and back through the circuit. On the other hand, whenever a voltage check indicates 0 volts, it means that there could be an open in the circuit path that's being used for the check. It's important to note, though, that an indication of 0 volts could also mean that the test instrument has malfunctioned. The proper operation of the test instrument can be verified by using it to check a point where you already know there is voltage. Basically, each test that's made in a circuit eliminates all of the devices and wiring either within the test path or outside the test path, depending on the result of the test. There's another important point to note about making voltage checks in a circuit. Any control devices in the circuit path being checked that are normally open, such as start push-button switches, should be closed when the check is made. There are several methods of applying the process of elimination to troubleshoot problems in electrical circuits. We're going to look at two common applications, the serial method and the half-splitting method. The major difference between these two methods is that the serial method is applied from one end of a circuit to the other, while the half-splitting method is applied from the middle of a circuit out. We can use the illustration that we just looked at to see examples of how each method can be used to troubleshoot an electrical circuit. Troubleshooting a problem in a circuit using the serial method involves checking the components in sequence, one at a time. This way, you can eliminate one component at a time as a possible cause of the problem. Although this method is logical and effective, it can be very time-consuming. For example, let's assume that there's a problem somewhere in this circuit, and that we know the circuit has the proper operating voltage. In this example, we'll use test point 8 as a reference point. To make sure that the reference point is good, we'll measure the voltage between L1 and test point 8. The voltmeter indicates full line voltage, so the wire connecting the load to neutral is good and can be eliminated as a possible cause of the problem. We'll start testing the circuit at test point 1. This check will determine if there is a complete path between L1 and test point 1. The voltmeter indicates full line voltage. This means that the wire connecting line lead L1 to control device A is good, so that wire can be eliminated as a possible cause of the problem. The next check would be at test point 2. The result of this test will indicate if the circuit's operating voltage is being applied through control device A. Again, the voltmeter indicates full line voltage. This means that control device A is closed and can be eliminated as a possible cause of the problem. The testing continues, moving along the circuit path one test point at a time until the cause of the problem is found. In some cases, you can eliminate possible causes of a problem very quickly by using a method called half-splitting. This method involves splitting a circuit in half and reduces the remaining number of possible causes of the problem by half. Assume that someone has picked a card from a deck and we have to guess what it is. The task of identifying the card begins with 52 possibilities. Using the serial method to identify the card could take as many as 51 guesses. However, with the half-splitting method, the maximum number of guesses is reduced to 6. Each question or test eliminates half of the remaining possibilities until only one is left. Here's how. First question, is it a black card? So it's a red card. Is it a heart? If it's not a heart, then we know it's a diamond. If the ace is high, is it an 8 or higher? Okay, is it a jack or higher? Is it a king or higher? Is it the queen? Since we've eliminated all of the cards except one, it must be the jack of diamonds. As we just saw, with the half-splitting method, each question or test reduced the number of remaining possibilities by half until only one possibility remained. Using the half-splitting method saved us time when we were trying to identify a card selected from a deck of 52 cards. Just think about what it can do for you when you're troubleshooting an electrical circuit. We can use the same illustration that we looked at earlier to show how the half-splitting method can be used to troubleshoot a problem. As we did with the serial method, we'll assume that a problem exists in this circuit and that we know the circuit has the proper operating voltage. We'll also assume that the wire connecting test point 8 to neutral has been tested and found to be good. By eliminating this wire as a possible cause of the problem, we can use test point 8 as the reference point for our voltage measurements. So now we're ready to start checking the circuit's components. To begin half-splitting, we need to split the circuit in half. The wire that connects control device B to control device C is in the middle of the circuit. This means that either test point 4 or test point 5 can be used to half split the circuit. We'll use test point 4. This test will check all of the components from L1 to test point 4. The voltmeter indicates full line voltage. By obtaining an indication of full line voltage at test point 4, we know there must be a complete circuit path from L1 to test point 4. This means that none of the components or wires in that path can be causing the problem. The next point to test should split the remaining portion of the circuit in half. So we'll make the next check at test point 6. This test will check the circuit from test point 4 to test point 6. This time the voltmeter indicates 0 volts. Since we know that there is voltage at test point 4, we can check the voltage at that test point to verify that the voltmeter is still operating properly. The voltmeter is still operational, so the indication of 0 volts at test point 6 means that the circuit's operating voltage, which was present at test point 4, is not reaching test point 6. Because the circuit's operating voltage is present at test point 4, but not test point 6, the cause of the problem must be between those two test points. Because the cause of the problem is located between test point 4 and test point 6, all of the circuit's components after test point 6 can be eliminated as possible causes of the problem. The last check that we need to make should split the remaining portion of the circuit in half. So we'll check the voltage at test point 5. This test will tell us if the wire between test points 4 and 5 is good. This time the voltmeter indicates full line voltage. This means that the circuit's operating voltage is reaching test point 5. Because there is voltage at test point 5, we can eliminate the wire connecting control device B to control device C as a possible cause of the problem. At this point, we've eliminated all of the components in the circuit except for control device C. Control device C is the only circuit component that is between test point 5, where the voltage was present, and test point 6, where the voltage was not present. Working through the circuit using the process of elimination has identified control device C as the cause of the problem. In the examples we looked at in this part, the desired test points in the circuit were all convenient and accessible. Actual circuits may not be as easy to split, and test points may not be easily accessible. However, the principles we covered apply to any circuit. What you need to keep in mind as you troubleshoot problems on the job is that the rigid systematic demands of a troubleshooting method may occasionally have to give way to practical considerations of how a circuit is laid out. Let's stop here and try a question on the process of elimination. In this topic, we introduced some of the fundamentals of troubleshooting as they apply to electrical circuits. We also saw two ways that the process of elimination can be applied to troubleshoot a circuit. Now would be a good time to try a couple of practice questions on this material. In this part, we're going to apply the steps of a basic troubleshooting procedure to finding and fixing a problem in a piece of electrical equipment. We're going to use this drill press as an example. This drill press is available for general maintenance shop use. It's powered by a 3-phase AC motor. The control circuit for the drill press contains components that are located in 3 separate enclosures: a fuse box, a control cabinet, and a push-button station. The fuse box contains 3 fuses and a power switch that has 3 knife blades. The fuse box door is interlocked with the power switch. This safety feature ensures that the fuse box cannot be energized while the door is open. The drill press's control cabinet contains a control relay and a set of normally closed temperature overload contacts. The control relay consists of a coil, 3 sets of power contacts, and a set of maintaining contacts. The temperature overload contacts are opened when the drill press's motor is in danger of being damaged by a thermal overload. The push-button station contains a push-button start switch and a push-button stop switch. We can use this illustration of the drill press's control circuit to see how the drill press operates. This circuit consists of a normally open push-button start switch, a set of normally open maintaining contacts, a normally closed push-button stop switch, a set of normally closed overload contacts, and the control relay's coil. The circuit receives its operating voltage through these lines. One phase of the AC voltage L1 is applied to the line on the left through one of the knife blades of the power switch and a fuse. Another phase, L2, is applied to the line on the right through another power switch knife blade and another fuse. When the start switch is pressed, its contacts close. This completes a path for current to flow through the start switch, the stop switch, the overload contacts, and the coil. The coil becomes energized when current flows through it. This causes the maintaining contacts to close. When the start switch is released, its contacts open. However, because the maintaining contacts are now closed, current can still flow through the coil, keeping it energized. Current will continue to flow until its path is opened or the source voltage is removed. The path will be opened if the stop switch is pressed or if the overload contacts open. The path will also be opened if any of the lines connecting the energized components open, or if any of the 4 energized components fail in the open position. The circuit's source voltage can be removed if the power switch is turned off, or if either or both of the phases is lost. Also, if either of the fuses for those phases opens, there will be no current flow through the coil. The electrician in this example receives a problem report concerning the drill press from his supervisor. The report says that the drill press doesn't operate properly. He gathers together the tools, test instruments, and safety gear that he'll need to work on the drill press. When the electrician arrives in the maintenance shop, he finds the faulty drill press. To help identify the problem, the electrician inspects the drill press and sees that there are no obvious signs of damage. He also sees that a tag has been placed on the drill to tell others that the drill press doesn't work properly. After making sure that the power switch on the fuse box is in the on position, the electrician tries to start the drill to verify that the actual problem is the same as the reported problem. The drill does not start, nor does it seem like any part of the drill or its motor is trying to start. In addition, the electrician does not hear the relay in the control cabinet making contact. At this point, the problem identified by maintenance shop personnel and confirmed by the electrician is that the drill press does not operate properly. Specifically, the drill press will not start. After the electrician identifies the problem in the drill press, he needs to take whatever steps are necessary to prevent the problem from causing any downtime, damage, or injuries. This drill press is not part of a system, so this problem cannot affect the operation of other equipment. Also, it's unlikely that other equipment could be damaged or that personnel could be injured because the drill press will not start. However, the electrician must take the appropriate measures to ensure the safety of other personnel while he works on the drill press. That's because he'll have to perform tests on exposed energized equipment to repair the problem. With the work area secured, the electrician begins the next step of the troubleshooting procedure, which is to determine the cause of the problem. It's possible that the problem is just that the feeder for this circuit has been shut off elsewhere in the plant. Making sure that a circuit has proper voltage is usually a good place to start troubleshooting. This circuit's operating voltage is applied to the fuse box, so that would be a logical place to make this check. However, this fuse box has a safety interlock that does not allow the fuse box to be energized while the door is open, and the electrician can't take voltage measurements inside the fuse box while the door is closed. To check the circuit's operating voltage, the electrician decides to measure the voltage at the point where the power lines from the fuse box enter the control cabinet. Taking this measurement will require the electrician to open the control cabinet door. Because the control cabinet contains energized electrical equipment, the electrician will need to use approved insulating gear to provide protection from electrical shock. After the electrician opens the cabinet door, he takes a moment to visually inspect the components inside. He sees that all of the components, including the thermal overload contacts and the control relay's coil, appear to be in good physical condition. He also sees that the overload contacts are closed. After the electrician finishes his inspection, he checks his voltmeter at a nearby wall outlet. To check the circuit's operation, he measures the phase-to-phase voltage where the power lines terminate inside the cabinet. He then measures the voltage from each phase to neutral. The results of these measurements indicate that the circuit has the proper operating voltage. Since the electrician has proven that the circuit has the proper operating voltage, he can eliminate the wiring leading into the fuse box, the components in the fuse box, and the wiring leading out of the fuse box into the control cabinet as possible causes of the problem. Also, he can eliminate the possibility that the power for this circuit has been shut off elsewhere in the plant. While the electrician has the cabinet door open, he decides to try to start the drill again while he watches the control relay's contacts. As before, the drill does not start. However, he has confirmed his earlier observation that the relay does not activate when the start switch is pressed. This tells the electrician that the cause of the problem is not in any of the wires leading from the control cabinet to the motor, the drill press motor, the pulleys that connect the motor to the drill, or the drill itself. At this point, the electrician has narrowed the location of the cause of the problem to the control cabinet, the push-button station, or the wiring that connects the two. In this example, the power switch components in the fuses have already been eliminated as possible causes of the problem. The remaining possibilities are the start switch, the stop switch, the overload contacts, the control relay's coil, and the wiring that connects these components to each other and to the circuit's operating voltage. So far, the electrician has seen that the coil is in good physical condition. And he has also seen that the overload contacts are in good condition and appear to be closed. However, none of these observations prove that these components are electrically sound. The electrician knows from previous experience that mechanical components, such as switches and contacts, are more likely to fail than electrical components, such as wiring or a coil. However, he does keep in mind that it's easy for wiring to become loose at connection points. That's because of the vibration that's common in most facilities. In this shop, though, there isn't as much vibration as there is in other locations in the plant. The electrician decides that either of the two push-button switches is more likely to have failed than the overload contacts. That's because the push-button switches get used more than the overload contacts. In addition, the overload contacts at least appeared to be in good condition earlier. The electrician does not have as much information regarding the push-button switches. The electrician decides to continue by testing for voltage inside the circuit. He'll use the right side of the coil as the reference point for his tests, since it's connected directly to line lead L2. To half-split this circuit, the electrician should test for voltage between the stop switch and the overload contacts. However, one end of the wire that connects these two components is in the push-button station, and the other end is in the control cabinet. Since the control cabinet is already open, the electrician decides to test for voltage at the overload contacts. The electrician presses the start switch and reads 0 volts on the voltmeter. He verifies that the voltmeter is still operating by measuring the phase-to-phase voltage in the control cabinet. The reading of 0 volts indicates that voltage is not getting to the overload contacts. This means that the problem is in the left half of the circuit. So the cause of the problem is either in one of the two push-button switches or in the wiring that's connected to the switches. Since it's more likely that the problem is in one of the two push-button switches, they'll be checked first. The electrician can check the switches by making voltage tests with the power to the circuit turned on, or by making continuity checks with the power turned off. Because it's safer to work on a circuit that is not energized, the electrician turns off the power switch. To be sure that the circuit is not energized, the electrician measures the voltage at the point where it enters the control cabinet and reads 0 volts at each phase. Then he verifies that the voltmeter is still operating properly. This confirms that the voltage to the circuit has been shut off. The electrician thinks that the stop switch is more likely to have failed than the start switch. That's because, as a normally closed switch, it has current flowing through it more often than the normally open start switch. So he decides to check the stop switch first. After closing the control cabinet door, the electrician opens up the push-button station. After setting up his multimeter to check continuity, he holds the test probes together. The display and the audible tone tell the electrician that the instrument can indicate a closed circuit path. Then he holds the test probes apart. The display's indication and the lack of an audible tone from the multimeter tell the electrician that the multimeter can indicate an open circuit path. The electrician connects the test probes to the contacts of the stop switch. The multimeter indicates that the stop switch is open. Under these conditions, the multimeter should not be indicating that the normally closed stop switch is open. Since the electrician has determined that the cause of the problem is a defective push-button switch, he can move on to the next troubleshooting step, which is to correct the problem. Before he leaves to obtain the replacement push-button switch, he needs to ensure that the work area is secured. He does this by locking and tagging the power switch. After the electrician returns, he installs the new switch. After the electrician has replaced the faulty component, he needs to return the drill press to normal operation. After removing the lock and tag, the electrician sets up the drill press to operate again, and then tries to start the drill. It works, so the problem has been fixed. After the electrician takes down the signs and barricades, he informs the necessary personnel that the drill press has been fixed and is ready to be returned to service. Then he completes the problem report so that he can return it to his supervisor. Well, in this part, we saw how the steps of a basic troubleshooting procedure can be applied to troubleshooting a problem in a piece of electrical equipment. Now's a good time to check your understanding of the material we covered in this part. In this part, we're going to apply the steps of a basic troubleshooting procedure to show how you can locate and repair problems in electrical systems. As an example, we're going to use a process that has two fly ash handling systems. These two systems normally operate separately, but they can work together if the valves in the systems are lined up in certain arrangements. Fly ash is a byproduct of the coal that's been burned to heat the water in this facility's boilers. The general operation of these fly ash handling systems is similar to other systems that move small particles such as dust, grain, or feed. We can use this simplified illustration of the fly ash handling process to see how it operates. The process has two nearly identical systems, which we'll call System A and System B. Each system consists of a group of hoppers, a collector, and a silo. Each system uses a vacuum pump, which is not shown, to suck fly ash from the hoppers into the collector, and a pressure blower, which is also not shown, to blow the fly ash from the collector into the silo. To add a degree of flexibility, the process contains two collector crossover valves and two silo crossover valves. These crossover valves, which are sometimes called diverter valves, allow the fly ash to cross over from one system to the other. A crossover valve has one inlet port and two outlet ports. Only one of the valve's outlet ports is open at a time. The other outlet is closed. Changing the position of a disc inside the valve changes which outlet is open and which outlet is closed. Therefore, there are two possible paths for the fly ash through a crossover valve: the normal straight-through path or the crossover path. These crossover valves can change the flow path of the fly ash as it moves through the process. During normal operation, each system works independently of the other, so there are two separate flow paths for fly ash in this process. Sometimes, though, it's necessary for one system to use part of the other system. For example, if the B collector is down for maintenance, the process's controls can be set up to route fly ash from the B system hoppers through the collector crossover valve to the A collector, and onto either the A silo or the B silo, depending on how the silo crossover valve is positioned. A major characteristic of this type of process is that all of the equipment in the process has to be properly set up in order for any of the process to operate. The main difference between the two systems is that the A silo can also be used as a backup silo for bottom ash from another process. Bottom ash is another byproduct of burnt coal. Bottom ash can flow into the A silo when this gate valve is open. The electrician in this example first hears of the problem in the fly ash handling process when he receives a call from his supervisor. The process was operating normally using the B system when a problem in the B silo forced a shutdown. The process operator tried to start up the process with the B collector crossed over to the A silo, but he was unable to finish the procedure because of another equipment malfunction. With no place to put the collected fly ash, there isn't much time before the plant will have to begin shutting down boilers. By the time the electrician returns to his shop, a problem report has been delivered. The electrician uses it to get more information about the problem. He gathers the tools, test instruments, and safety gear that he'll need for this job. To take the first step in troubleshooting this problem, The electrician talks with the operator who reported the problem. At the process's control panel, the operator repeats the startup procedure that he tried when he attempted to route the fly ash in the process's B collector to the process's A silo. As they attempt the startup procedure again, the electrician sees for himself that the process does not operate. After the electrician has identified the problem, he takes steps to prevent unnecessary downtime, damage to plant equipment, and injury to plant personnel. In this case, he talks with the appropriate personnel working in the affected units. He lets them know what he'll be doing, and he finds out that repairs have already been started on the problem in the B silo. With that silo out of service, he's told that in about 30 minutes other workers will have to begin shutting down the boilers. Having informed personnel in units that are affected by this problem, the electrician focuses on the next basic troubleshooting step, which is to determine the cause of the problem. The electrician attempts the same procedure that the operator went through to start up the process, paying particular attention to the control panel's indicator lights. It's possible to gather a lot of information about a problem using the devices that are already in place. The indicator light for the appropriate silo crossover valve did not come on. The indicator lights for the B system's vacuum pump and pressure blower did not come on either. The electrician knows that this process is designed to operate only when all of its valves and other equipment are set up properly. We can use the illustration that we looked at earlier to get a better idea of what the electrician has learned from the control panel indicators. Because the B system was operating normally before the B silo had to be taken out of service, the electrician can eliminate the B system hoppers, the B collector, and the flow path between the two as possible causes of this problem. He can also eliminate the vacuum pump and the pressure blower for the B system. Based on this information, the electrician concludes that the problem is located either in the B system silo crossover valve or in the circuitry that controls the valve. The electrician is able to eliminate most of the components in this process because he knows how the process is designed to operate, and he observed the process's control panel indicators. This saved him a lot of time narrowing down the scope of the problem. Now the electrician can focus on the portion of the process that controls the operation of the B system silo crossover valve. This illustration represents the control circuit that he plans to focus on. This control circuit contains 3 limit switches, an indicator light, and a control relays coil. The circuit's operating voltage is available on these lines. The line on the left is energized at 110 volts AC, and the line on the right is connected to neutral. Limit switch LS40 is closed when the process routes fly ash from either the A collector or the B collector to the A silo. This limit switch is open when the process routes material from the bottom ash unit to the A silo. Limit switches LS38A and LS38B are open when the process is in its normal fly ash routing mode. These limit switches are closed only when the process is in the crossover mode that routes the fly ash from the B collector to the A silo. When the process is operating properly and all 3 limit switches are closed, the silo crossover indicator light comes on and the control relays coil is activated. When the control relays coil is activated, the control relays contacts are also activated. This change in the state of the contacts allows other devices in the process to operate. In this situation, the electrician knows that when the crossover is attempted, the indicator light does not come on, and other devices, which are partially controlled by the relay, are not activated. Since both the indicator light and the relay's coil require that all 3 limit switches be closed, the electrician decides to check the limit switches and the wiring that connects the limit switches to the light and the coil for an open. To do this, he goes to the wiring termination panel for the circuit and sets up his multimeter to measure voltage. Since he'll be working near exposed energized electrical equipment, he will use approved insulating gear to protect himself against electrical shock. To make it easier to follow the voltage test that the electrician will perform on the circuit, we'll number each test point. We'll use these numbers to refer to the locations that the electrician tests. The first test will be to verify that the circuit has the proper voltage. The electrician will use test point 10 as the reference point for all the tests. and he'll perform this test at test point 1. The voltmeter indicates full line voltage, so this circuit has the proper operating voltage. Next, the electrician decides to half-split the circuit by testing for voltage at test point 5. The result of this test will indicate if the voltage at test point 1 is also present at test point 5. At test point 5, the electrician measures 0 volts. He verifies that the voltmeter is still operating properly by reading full line voltage at test point 1 again. A measurement of 0 volts at test point 5 means that the circuit's operating voltage, which is present at test point 1, is not reaching test point 5. This means that there is an open somewhere between these two test points. It also means that none of the components between test point 5 and test point 10 can be causing this startup problem. The electrician half-splits the circuit again by measuring the voltage at test point 3. This test will check the path from test point 1 to test point 3. Here, the voltmeter indicates full line voltage. This tells him that the voltage at test point 1 is also present at test point 3. This means that this portion of the circuit can be eliminated from consideration as containing the source of the problem. So the problem must be an open between test point 3 and test point 5. The electrician splits the remaining portion of the circuit in half by checking test point 4. This check will tell him if the connection between test point 3 and test point 4 is good. At test point 4, the electrician reads full line voltage. Reading full line voltage at test point 4 tells the electrician that the voltage at test point 3 is also present at test point 4. This eliminates the wire between the two test points as a possible cause of the problem. The only remaining possibility is that the open in the circuit that's causing the startup problem is between test point 4 and test point 5, which is the limit switch LS38A. This switch should be closed. However, it appears that the limit switch is open. The electrician goes to the silo crossover valve that's associated with the suspect limit switch. During his inspection, he finds that one of the limit switch control arms has become loose. Since the actuator cannot make contact with the control arm, the limit switch cannot change states from open to closed. Now that the electrician has determined that the crossover valve has malfunctioned, he needs to correct the problem. This valve operates using air pressure. The circuit has been locked and tagged, so from an electrical perspective, it's safe. However, to be considered safe to work on, all sources of hazardous energy must be removed, and since this is an air-operated valve, that includes air pressure. The electrician turns off the air supply to the valve. Then he opens the bleed valve to release the air pressure in the valve. He corrects the problem by cleaning the valve and repositioning the loose limit switch control arm. Then he closes the bleed valve and turns the valve's air supply back on. He switches the valve to its manual override mode to test the operation of the valve. Then he returns the valve to its automatic mode. All that's left to do is return the circuit to normal operation. At the control panel, the electrician attempts the startup procedure again. This time, the silo crossover indicator light comes on, but the other devices in the process are still not activated. The electrician knows that he has re-established a complete path for the control circuit because the silo crossover indicator light came on. However, that does not mean that there is not another problem in the process. Since the crossover mode is not used very often, it's possible that more than one fault could have developed since the last time it was used. Faced with this new problem, the electrician should go back to the third step of the basic troubleshooting procedure and determine the cause of this problem. Returning to the control circuit illustration, the electrician decides that the best thing to do is make sure that the rest of this circuit is working properly before moving on to any other part of the system. He knows that there is a completely closed path from test point 1 to test point 10 because the indicator light is on. He also knows that his previous work did not conclusively prove that the relay's coil was operating properly. All he did was eliminate the coil as a possible cause of the first problem. And he knows that there is a big difference between eliminating a device as a possible cause of a problem and proving the device is good. Since the rest of the circuit is operating properly, the electrician knows that any problem that remains in this circuit must be in the relay's coil or in the wiring that connects the coil to the circuit. So the electrician returns to the wiring termination panel to check the relay. During his visual inspection, he sees that the relay's indicator bar or target is not pulled in. This indicates that the relay is not energized. He also notices that there is a loose wire on one side of the relay's coil. Given the relay's location in the plant, it's very likely that vibration caused the wire to become loose, probably during the extended period of time that the relay was not being used. Now that the electrician has determined the cause of the second problem, he must correct it. After verifying that the relay and the wire are not energized, the electrician tightens the wire onto the relay. After he finishes, he returns to the control panel to attempt to return the circuit and the process to normal operation. The electrician attempts the startup procedure again. This time, after the silo crossover indicator light comes on, the vacuum pump and the pressure blower each turn on. The process is operating properly. The electrician tells the process's operator that everything is working normally again, and he notifies the appropriate personnel that the fly ash handling systems are operational. After he returns to his shop, he completes the necessary paperwork so that he can return it to his supervisor.